Probably the most infamous example of a proof by induction that mathematicians tend to think of whenever we think about induction is this result right here. This is the result that says that for all natural numbers n, if I add up the sum of the first n natural numbers, starting from 1, so 1 plus 2 plus 3 plus all the way up to n, that sum is equal to n times n plus 1 over 2. And there are a variety of different ways to make a good heuristic argument for why this should be the case. One of the most famous ways to see this, right? Let's just take an example. 1 plus 2 plus 3 plus... So this is the formula that we're supposed to try to justify, n times n plus 1 divided by 2, and that this is supposed to be true for any natural number n starting from 1. Right? And so one of the classic heuristic arguments for why this thing should be true, I'll just illustrate by an example. Let's suppose I choose n equals, 9. And so I want to know, what do I get when I add up the first 9 numbers, starting from 1, first 9 natural numbers? Does anybody know what a quick and dirty way of discovering this sum is? Have you encountered this before? So on the one hand, we could look at an arithmetic model. And what I mean by that is just by looking at the numbers, maybe we can come up with a nice way of sort of grouping them together, reordering the terms in this sum to try to understand it better. And so what I might notice if I look at this sum for a while is that the least and the greatest numbers in this line here, 1 and 9, if I add those up, those are going to give me a 10. So I can get a 10 by taking the first number and the last number in this sequence. But then I can continue that game by taking the next least and the next greatest, the 2 and the 8. Those are going to give me a 10 also. And so on and so on. And so one way of making this argument is just by trying to pair up the least and the greatest over and over again until we have accounted for all possible pairs. And so if I look at this example, I have a total of 9 summands, 9 numbers that I'm adding up together, right? And if I pair off the first and the last, and then the next first and the next most last, and so forth, I'm going to end up getting a total of, well, I'm going to get a total of 4 pairs, aren't I? The last pair being this 4 and this 6. And then I'm going to have one leftover 5 there in the middle. So I'll have to try to figure out how to account for that. But anyway, that's sort of one way to be systematic about it. And then I can just add up those pairs. I get 4 10s and a 5. And that gives me 45. So this is supposedly, I don't know if this is an apocryphal story or not, but this is supposedly the story of young Leonhard Euler, the later famous mathematician. When he was in grade school, he was assigned as a punishment by his teacher for being too precocious, apparently, that the teacher wanted Lenny to go sit in the corner of the classroom and add up all the numbers from 1 to 100. She figured it would take him the best part of the afternoon to finish. And of course, Lenny finishes it after a minute and then comes back and says, oh, obviously it's, what would it be, 5,050 or something like that. And the teacher asks, well, how did you do that so quickly? And it was a strategy similar to this one. So let's try to generalize the process that Lenny Euler would have just used, the one that we just used. See if we can arrive at this formula, right? Why is it n times n plus 1 over 2? So what we've noticed, right, is that we do have a bunch of pairs that added up to 10, but then we had this one that was left over that just accounted for a 5. So what would happen? We had a total of 9 summands, right? And it ended up being 4 pairs of 10. And that's n plus 1, right, in this example. So we had n plus 1 appearing this many times, plus a single 5. Right. But another way to see what that 5 is that 5 is just an n plus 1 over 2. Right? When I have this one that's left over, then that number that's going to be left over, the median of this set of natural numbers, right, is just going to be 1/2 of the total number of numbers that I have added to 1. And so what I get when I add these up, we believe this is going to give me n times n plus 1 over 2. But actually I want to, again, while we're still in the realm of trying to come up with arguments for why this should be true that don't involve an induction proof, we'll get there, here's another argument that I happen to like quite a bit. Let's take this same sum of 1s through 9s, and let's represent it graphically instead of arithmetically. So what am I doing? I'm taking 1 dot, and I'm adding it to 2 dots, and then I'm adding 3 dots, 4 dots, 5 dots. So I'm going to kind of arrange them in a fashion like this. And when I arrange them in this fashion, we can see why we call numbers that have this format triangular numbers. There are numbers that we can get by arranging the integers in one of these triangular fashions. How far out have I gotten? That's 8. And so I just need one more row that goes out to 9. And so here is all 45 of my dots, right, arranged in rows of 1, 2, 3, up to 9. Right, so this is one way of looking at it. And so how could I know how many dots that I have here? Well, I guess we could ask, how many rows do I have? And the number of rows I have over here is 9, which again, we're going to think of that as my n, right? But then it's a little bit unclear why, or what I should do with the number of columns, right? Because it also looks like it would be 9. And if we're sort of thinking about this as the area of a triangle, then we're getting close, right? Because the area of a triangle is 1/2 the product of the base and the height. Except that in this particular triangle, both the base and the height are equal to 9. So that doesn't seem to be very helpful, because that would appear to tell us that it should be n times n over 2. Instead of n times n plus 1 over 2. And so there's a difference between finding the area of a triangle and counting the number of dots in a triangular number. So here's how we get around that particular objection. How we can do that is by repeating this same process, drawing out my triangular number one more time, but starting from the bottom at the end of this last row. So I'm going to put 1 dot right there, and then 2 dots above it, and then 3 dots above it, 4 dots above that, 5 above that. I think this is probably my favorite way of convincing somebody who doesn't necessarily even need to know any algebra about why this formula should work. I'm going to have to make a little space here. Dots, 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 dots. And so I still have a diagram of 9 rows. But now how many columns do I have? I have 10 columns, which is n plus 1. Right? And so if I want to know how many red dots there are, I might ask, how many total dots do I have in this diagram? And that, because we do know how to compute the number of dots in a rectangular array, which is what I have, right? The total number of dots is n times n plus 1. So total dots is n times n plus 1. But why do I divide by 2? Because I only wanted the ones that were red. And there are an equal number of red dots as there are green dots. I know that just because of, by construction, how I constructed this diagram in the first place, right? Is I started at the last row of the red dots by adding one more green dot on the end and then going backwards. So there are exactly as many red dots as there are green dots. And so if I want the red only, I'll divide by 2. So there is sort of a very naive way of kind of making this a procedural argument, right? If I wanted to know, if I had a bunch of rocks or marbles or something at my disposal and I wanted to come up with a formula for this, this might be a way that I could do it, right? Except, of course, the problem is that just drawing out these dots doesn't actually prove anything. Right? It's not an argument that's likely to convince a mathematician who is insistent on sort of first order, first principles logic, right? I've shown you why the sum of 1 through 9 is equal to 45 in a couple of different ways. But you don't necessarily have to buy my argument for the case where n is equal to 15, or the case where n is equal to 250,000. You don't have to buy those arguments, no matter how many specific individual cases that I present to you. So what we would like to be able to do is to write a proof of this statement, which is going to be valid proof for all possible natural number values of n. So there are infinitely many statements that we would have to prove in order to be completely convincing, right, that this method is always going to work. And any skeptical mathematician should always be asking that question: how do I know this always works? And a proof by mathematical induction is a way to provide a proof of a statement which is quantified on an infinite set of natural numbers. In this example, it's the set of all the natural numbers themselves, starting from 1, 1, 2, 3, all the way up to infinity. So here's how a proof by the principle of mathematical induction would look for this statement. So a proof by mathematical induction is a bit like knocking over an infinite set of dominoes, right? So we have this infinite set of natural numbers starting from 1 and extending all the way to infinity. And I want to show that I can knock over this entire sequence, this entire infinite sequence of dominoes. And so there's really two things that we have to prove in order to prove that every domino in this list does indeed topple. The first is that I should think about whether it's the case that every domino which falls, let's say that the kth domino falls, will necessarily knock over the domino that comes after it. Is it always the case that any domino that falls over is going to hit its neighbor and make its neighbor fall? Because if there's a little gap in my set of dominoes, right, and one of the dominoes can fall and the other one can stay standing, well, then we don't know that all the dominoes will fall, right? So probably where we do the most work in a proof by induction is right there, showing that if you choose any arbitrary domino in this sequence, that if that domino is to fall, then the next one in the sequence will also fall afterwards, right? And that is a conditional proposition. That's an if-then statement. If the kth domino falls, then the k plus first domino will fall. And so the core of an induction proof is a proof of that implication, that if the kth proposition is assumed to be true, then it must follow that the k plus first proposition is true. So if the kth domino falls, then the k plus first domino must fall. That's where we do most of our work. And that's what shows that these dominoes are all going to fall together. But it's not complete unless we also show that we can push over the first domino in the sequence. So we also need to explicitly show that whatever is the first domino in my sequence, which in our example here, because we're quantified over the natural numbers, our first domino is going to be the n equals 1 domino. I need to show specifically that that first domino can be toppled. Specifically show that the first statement in my sequence of quantified statements is true. And if I show both of those things, show that every falling domino knocks over the next one in line, and also that the first domino in the sequence can be toppled, then the principle of mathematical induction guarantees for us that every domino in that sequence has fallen. And so we've proven the statement is true for all natural numbers. So what might I do first? So the names of these three components in any induction proof are, first of all, an inductive hypothesis. This is the assumption that the kth domino can fall, right? If I assume that the kth domino has fallen, then I need to prove that the k plus first domino will also fall. And that's called the induction case, or the inductive step in an induction proof. And this is where most of the work happens, right? We have to prove that this domino falling implies that domino falling, usually by means of a direct proof, but I'm sure that there are plenty of proofs by induction out there that also run this argument indirectly by contradiction. It's a little bit harder to do, though, because most often what you're doing is you're explicitly making an assumption that the kth domino has fallen. And so that lends itself to a direct form of proof for the inductive step. And then completely separately from all that is the base, what we call the base case. That's the case that shows specifically, concretely, that the first domino that we claim will fall does in fact fall. The first statement in my sequence will specifically prove that it's true. So let's start from there. This is where most people start an induction proof, even though, again, logically it's totally separate. from the inductive step. But we'll try the base case. And the base case here, again, because the smallest natural number that we're trying to prove the statement for is n equals 1, we'll evaluate this claim and whether it's true in the case where n is equal to 1. One of the hard things I find for students in trying to get a feel for induction is just understanding what is intended by a statement, a claim that looks like this, in a funny case like n is equal to 1. What does it mean to do 1 plus 2 plus 3 plus ... plus 1? And that's a limitation of how mathematicians use notation to express themselves. I think very often a better way to think about a statement like this is just to sort of ask yourself in words, well, what's being done over here on the left-hand side? I would say what's being done is we're adding up the first n natural numbers, starting from 1. And so if I choose n to itself be 1, what we're doing is we are adding up the first 1 natural numbers. How many natural numbers are we adding together? Just 1. And so the fact that there's a plus 2 and a plus 3 and there's other dots in the middle here is completely not relevant to our base case. In our base case, we only have one summand on the left-hand side, and that one summand is just 1. So very often that's the trickiest part, is just interpreting what is intended by this general claim well enough so that you can figure out what the base case should actually look like. And in the base case here, I would say the left-hand side of this equation will be equal to 1, the sum of the first 1 natural numbers. But then the right-hand side, n times n plus 1 over 2, well, when n is equal to 1, I can just evaluate 1 times 1 plus 1, all divided by 2. That's 1 times 2 over 2. That's equal to 1. And so both the left-hand side and the right-hand side of this equation are equal to 1, and so we conclude the base case is true. This is the thing that students love about the base case, is it's very concrete most of the time, right? It leads you down to an equation whose left and right-hand sides are just numbers, and they end up being exactly the same number, so we conclude the base case is true. It's very cut and dried. It's very difficult to argue very often with somebody's argument on a base case. And so where all of the action happens is then establishing the inductive step, the induction case. Because the induction step is our chance to assume that the kth domino has fallen. So we're going to take on faith. We're going to ask the reader to presume that domino number k has fallen for an arbitrary k. So we have to leave that k completely not concrete at all, right? So for an arbitrary k, we will assume that the kth domino has fallen. And so we'll evaluate this claim with a k in place of an n. So the sum of the first k natural numbers is equal to k times k plus 1 over 2. And we assume that to be true. Okay? So we're setting ourselves up for a direct form of proof. We assume p, and then we use p to try to prove q. And here q is the statement that the k plus first domino has fallen. So we'll evaluate the statement with k plus 1 in place of n. Right? The sum of the first k plus 1 natural numbers is equal to k plus 1 times k plus 1 plus 1 divided by 2. So I always recommend writing out both the form of the kth proposition and also the form of the k plus first proposition. Write them both out, because the key to a successful proof by induction is figuring out how to discover from within the thing that we don't know is true, discover the form of something which we do know is true. How do we relate an expression, for example, that we have in one of the formulas that we're working with in our k plus 1 case? How do we relate that back to the thing which we have assumed to be true as part of our inductive hypothesis? So the entire key is discovering the inductive hypothesis within the thing that we don't know yet is true. Figure out how to apply that inductive hypothesis. Because if you get to the end of a proof that you thought you were doing by induction, and you haven't actually explicitly used that hypothesis somewhere along the way, then either you didn't do it right, or you did it right, but it wasn't actually an inductive proof. Okay? So this is also how we recognize a proof as being a proof by induction, is it has to use that hypothesis somewhere along the way. And so the key insight often comes as something like this. I have this statement over here in the green that I don't know whether it's true, but I'm trying to demonstrate that it is, right? That the sum of the first k plus 1 integers is k plus 1 times k plus 2 divided by 2. I don't know that that's true, but I do know that the sum of the first k plus 1 integers must include the sum of the first k integers. Natural numbers, sorry. So I cannot add 1 plus 2 plus 3 all the way up to k plus 1 without first adding 1 plus 2 plus 3 all the way up to k. That is the key insight in an inductive proof like this one. Because once I realize that, oh, I have to have gone through k before I got to k plus 1, now I look at this expression and say, oh, look, 1 plus 2 plus 3 plus up to k, I know something about 1 plus 2 plus 3 plus up to k. Right? I have assumed in my proof something about the sum of the first k natural numbers. Namely, I've assumed that that sum of the first k natural numbers is k times k plus 1 over 2. That's the step right there where we have applied explicitly the induction hypothesis. And what it's done is it's gotten rid of this troublesome ... that's a part of the thing that I'm trying to prove. Right? And it's given me a concrete algebraic expression in terms of k. And since we've assumed the inductive hypothesis is true, we know for sure in my proof that I can replace that sum with k times k plus 1 over 2. And then returning to what I have above, I need to add k plus 1 to that, and then try to do whatever algebra I would need to do to show that in fact this is equal to the thing that I was hoping that it was equal to at the end of the day. And so that algebra can be however you like. I like to, for example, just factor the k plus 1 out of both of these terms. If I do that, the cofactor is k over 2 plus 1, just factoring the k plus 1s out of these two terms here. Then finding a common denominator for k over 2 plus 1, that will give me k plus 2 divided by 2. And when I multiply k plus 2 divided by 2 times k plus 1, sure enough, I get k plus 1 times k plus 2 divided by 2. And I've demonstrated then that my inductive case, my inductive step is true, that the k plus first proposition, the k plus first domino, will fall as soon as I topple, assume true, the kth. And that comprises a complete proof by mathematical induction. And so at the end of this proof, we include a sentence that says something like, by the principle of mathematical induction, we have proven that for all natural numbers n, that the sum of the first n natural numbers is n times n plus 1 over 2.